NASA has released a new batch of images from the depths of space, captured by the James Webb Space Telescope. These are among the first glimpses of the universe in its infancy, showing distant galaxies whose light has traveled more than 13 billion years to reach us. The first images revealed faint specks of light, each a messenger from a time shortly after the Big Bang, offering a journey not just across space, but back through time itself. The James Webb Telescope does more than collect light. It unveils structure, motion, and formation, revealing the raw cosmic canvas being painted by forces we are only beginning to understand. Its high-resolution infrared images allow astronomers to peer through cosmic dust and see galaxies that are surprisingly mature, massive, and complex, far earlier than conventional models predicted. These findings challenge long-held assumptions about galaxy formation, suggesting that the universe may have been far more efficient at creating order from chaos than scientists ever imagined. Some galaxies Webb has captured formed just 300 to 400 million years after the Big Bang, a timeline that contradicts established models. Instead of chaotic blobs, these early galaxies already show spiral arms, starburst regions, and even signs of active supermassive black holes. Such discoveries suggest that cosmic matter coalesced more rapidly than anticipated. Dark matter, previously considered a static scaffold for galaxy formation, might play a more dynamic role, or there may be unknown physical processes at work, shaping the infant cosmos in ways we do not yet understand. Webb has also captured galaxies in the act of merging, revealing the dynamics of collisions with unprecedented clarity. Tidal forces, gas inflows, and emergent spiral structures show how galaxies grow through accretion and interaction, painting a picture of an early universe teeming with activity rather than a quiet, diffuse expanse. These observations offer a living laboratory for studying the forces that shape the cosmos, giving insight into the conditions that allowed stars, galaxies, and perhaps even planets to form so quickly. Spectroscopic instruments on the telescope provide another layer of insight, revealing the chemical composition of these ancient light sources. Webb has detected carbon, oxygen, and even iron in galaxies that existed so early that several generations of stars must have already lived and died. This pushes the timeline of stellar evolution backward, forcing scientists to reconsider how quickly stars and heavy elements formed in the early universe. Beyond individual galaxies, Webb has glimpsed the large-scale architecture of the cosmos. Proto-galactic filaments, the scaffolding connecting clusters of galaxies, are already in place, suggesting that the universe's structure emerged faster and more elegantly than previous models predicted. Gravitational lensing, where light bends around massive clusters, further reveals the distribution of dark matter, turning these natural magnifying glasses into tools for mapping the invisible skeleton of the cosmos. Webb's observations also shed light on the epoch of reionization, when the universe transitioned from neutral hydrogen to ionized gas, allowing light to travel freely for the first time. The telescope's sensitivity has allowed astronomers to chart this process in exquisite detail, revealing starburst activity that shaped the early cosmos and illuminated the darkness. Massive gaseous halos surrounding early galaxies hint that feedback from stars and black holes was already influencing their surroundings, regulating star formation and the flow of matter even in these primordial times. In some of the most distant galaxies, Webb has found signs of supermassive black holes forming earlier than expected, growing alongside their host galaxies with astonishing speed. These early behemoths challenge standard models of black hole growth and suggest that our understanding of cosmic evolution is far from complete. The James Webb Space Telescope has only just begun its exploration, and yet it has already rewritten what we know about the early universe. Every photon it collects is a whisper from a time when the universe was young, dense, and alive with energy. The data it provides will take decades to fully analyze, offering humanity an unparalleled view into our cosmic origins. Each observation, from the smallest proto-galaxy to the largest filaments, forces us to reconsider the speed, efficiency, and elegance with which the universe built itself. Through Webb, we see a cosmos that is not a slow, chaotic experiment but a place of astonishing efficiency and beauty. Galaxies bloom almost as soon as the universe exists. Stars ignite with urgency, structures form with precision, and the hidden frameworks of dark matter and gas weave together to create the cosmos we inhabit today. The telescope's discoveries connect us to this ancient past, revealing not just the history of distant galaxies, but also the conditions that allowed stars, planets, and life to emerge. With every new image and dataset, the James Webb Space Telescope brings us closer to understanding the universe's earliest moments. It reveals a cosmos more intricate, more dynamic, and more breathtaking than anyone imagined, challenging our assumptions and inspiring new questions about the very nature of space, time, and existence. The James Webb Space Telescope is revealing phenomena that were once purely theoretical. One possibility is the existence of direct collapse black holes, where massive clouds of gas collapse straight into black holes without forming stars first. Webb may be witnessing these events in real time, potentially providing the first observational evidence for this long-suspected but never-before-seen pathway of black hole formation. Even from billions of light-years away, the gravitational influence of these black holes is detectable, subtly affecting the motion of surrounding stars and gas. By analyzing this motion through spectroscopic data, astronomers can measure the mass and behavior of these ancient giants. These observations suggest that the co-evolution of black holes and their host galaxies began far earlier than previously believed, raising profound questions about the forces that shaped the first complex systems in the universe. Yet it is not only the massive and luminous objects that are important. Webb has begun detecting tiny, faint galaxies, dwarfs and protogalaxies, whose light is barely strong enough to register even in long exposures. These faint systems are critical for understanding the full spectrum of galaxy formation, revealing the small building blocks that eventually merge into larger galaxies. Their abundance near the edge of the observable universe suggests a kind of cosmic scaffolding, a population of seeds from which more complex structures grew. Despite their dimness, these small galaxies may have played a key role in the epoch of reionization, contributing collectively to the ionization of hydrogen and allowing light to travel freely across the cosmos. Webb is also exploring the intergalactic medium, the thin gas that permeates the space between galaxies. By studying how light from distant quasars passes through this medium, the telescope reconstructs its composition and thermal history. This gas acted as both a reservoir for future star formation and a stage on which galaxies and black holes reshaped their environment. Spectroscopic observations are revealing how matter circulated between galaxies and the intergalactic medium, creating a dynamic picture of cosmic evolution where even the space between galaxies is alive with processes that shaped the early universe. Time itself becomes a tool with Webb's observations. By examining galaxies at slightly different redshifts, astronomers can assemble a frame-by-frame sequence of cosmic history, almost like watching a slow-motion movie of the universe's growth. This temporal layering traces the formation of elements, the rise of large-scale structures, and the transformation of the universe from a simple plasma into a complex web of stars, galaxies, and voids. Even with this wealth of data, the question remains: what lies beyond the observable universe? Webb cannot see past this boundary, not because there is nothing there, but because light from more distant regions has not had time to reach us. This limit is temporal rather than physical, dictated by the finite speed of light and the universe's age. Still, Webb has pushed the boundary of observation closer to this theoretical limit than ever before, revealing an intricate mosaic of ancient light. The unseen regions beyond are likely just as rich with structure and mystery. Subtle anomalies in Webb's data are also prompting cosmologists to revisit the universe's geometry. Are space and time perfectly flat, or do they possess slight curvature visible only at the largest scales? Could the universe loop back on itself, or stretch infinitely beyond comprehension? Webb's measurements of galaxy clustering and light distribution may help answer these fundamental questions that have persisted since the dawn of cosmology. Webb's success relies on extraordinary technological achievement. Its instruments are cooled to frigid temperatures and positioned at the second Lagrange point, shielded from the heat and light of the Sun and Earth. This allows it to detect faint infrared signals with minimal background interference, making it uniquely capable of observing the faintest structures at the edge of the universe. At the heart of this exploration lies a profoundly human impulse: the desire to understand our origins and place in the cosmos. Every photon Webb collects enriches the tapestry of cosmic history, adding new layers to our understanding of matter, energy, and existence. As more data accumulates, some long-held theories may be revised or even discarded. Exotic forms of matter or energy, or unknown laws of physics in the early universe, could emerge from these observations. The edge of the observable universe is proving to be not an ending, but a beginning, a laboratory for discovery where new science is born. Philosophical questions also arise. If complex structures formed so rapidly, is the emergence of order a natural feature of the universe? Could the formation of stars, galaxies, and potentially life be an inevitable outcome under certain cosmic conditions? These questions sit at the intersection of science and philosophy, inspired by empirical data gathered from the deepest reaches of space. Webb continues to refine the map of the early universe, isolating key epochs, comparing growth rates, and measuring cosmic acceleration with unprecedented precision. It may uncover older galaxies and approach the so-called cosmic, dark ages, a time before stars and galaxies existed, providing insights into how the universe transitioned from emptiness to structure. Each new image brings not emptiness, but intricate networks of light and matter. Among Webb's most remarkable discoveries are the complex interactions between gas dynamics and star formation. High-velocity winds from early starbursts and growing black holes regulate star formation by shaping the surrounding medium. Metals produced by early stars are expelled and recycled, enriching future generations of stars and planets. Observations of globular clusters forming within these early galaxies provide rare insight into how dense stellar